Welcome back. Today is Le Chatelier's principle. Now, this principle deals with equilibrium, which we've already talked about, but it talks about a specific part of equilibrium, and that's changing what we can create in our chemical reaction. So first off, Le Chatelier's principle is stressing a system. Now, you know what stress is because you are in high school and you have tons of homework to do, right? And some of you will have more in the future, and then you go to college and then you get jobs. Stress is everywhere. But what happens when we start feeling stressed? We start trying to alleviate that stress somehow. So if I start feeling stressed about making sure that one of my lessons is planned correctly and that it's, understandable and everything like that, I'm going to take a break and maybe I'll go walk around the neighborhood. I'll go play a game. I'll go talk to my sister. I do something that helps me relieve that stress so that I can go back to whatever I'm doing and I'll be okay. Just like when you guys have homework, some of us just stop doing the homework, but others of us will decide to take a break from the homework. We go out, we go, play soccer, we play baseball, we play whatever, and that helps relieve that stress so that when we come back to the homework or whatever we found was stressful before, we have a little less tension built up and we can handle it better. Well, chemical reactions are the exact same way. So when we're talking about equilibrium, we're talking about the fact that both rates are going at the same amount, right? Our concentrations stay constant. They don't have to be the same, but they stay constant on both sides. And reactants are going back and forth, and they're at what we call equilibrium. They are equal. Well, the stress in the case of chemical reactions is anything that upsets the equilibrium of a reaction. So anything that's going to cause one side of a reaction to not be equal with another side of a reaction. All right? So as a review, let's review systems at equilibrium. Systems at equilibrium are either product favored or reactant favored, which means that at equilibrium, we're either making more products or more reactants, but our rates are the same. Okay? So how can you tell? Remember, our KEQ value is how we tell. So KEQ is equal to the concentration of our products over reactants. And we know that if products are favored, our KEQ is going to be very large because our numerator is big. However, if reactants are favored, our KEQ is going to be very small because our denominator is bigger. So the way we can tell if products or reactants are favored is by looking at our KEQ, the ratio of products to reactants. All right, the second thing about equilibrium is they can be shifted either way to make products or reactants by what we call stressing a system. So for instance, if I'm talking about a reaction, reactant goes to product, I'm going to say, well, what happens if I add more reactant, okay? So this guy is at equilibrium. They're both going back and forth. Oh, forgot that part. My bad. So they're both going back and forth. Reactants to products, products to reactants. But then I introduce a whole lot of reactants. I increase my reactants. Okay? What's that going to do to my reaction? Well, now my reactants are too much. And my system's not at equilibrium again. So what do I have to do? I have to make more product. So if I add more reactants, it's going to cause my equilibrium to shift to make more products. Okay? Well, what if I remove a reactant? Okay, so let's say that I take some reactant away. Well, now which side is unbalanced? The reactants are. So my products have to make more reactant in order to fill that hole. So what's going to happen to my products? They're going to have to decrease, and equilibrium will shift to make more reactants. Okay? So whatever I do to one side, the other side is going to have to make up in order to get back to equilibrium, because that's where we're trying to be. Now the same thing is true for backwards. If I increase my product, then my reactants are going to have to start making more. All right, so my equilibrium is going to shift to my reactants. And then if I decrease my reactants, well, my products are also going to have to decrease, and I'm going to have to make more of the other. All right, so whatever I do to one side, I have to shift and go to the other side. So over here, adding more reactant will cause equilibrium to shift towards products. Removing a reactant will cause equilibrium to shift towards reactants so that they can fill back up. Adding more product will cause equilibrium to shift towards reactants. And removing a product will cause equilibrium to shift towards products. All right, whatever I do to one, it's going to have to compensate and go back and do to the other. Okay, so let's see how concentration is affected on an actual reaction, all right? Carbon monoxide and hydrogen. Well, if I were to add more hydrogen gas, so I'm going to come over here and I'm going to put more hydrogen gas in my reaction. Which way will equilibrium shift? Equilibrium is going to shift to make more products. I'm going to have to make more products in order to get equilibrium to balance out again. I need to use up that extra hydrogen. Now, if we remove CH4 from the system, equilibrium is going to shift back to CH4 because I've made a hole over on my product side, and so my reactants are going to have to start making more products to fill that hole. So they're going to shift to products, make more products. And then if carbon monoxide is removed from the system, well, I look and my hole is over on my reactant side. I need to fill that side. I need to equalize again, and so my products are going to make more reactants. Okay? So whenever you're dealing with Le Chatelier's principle is just that a reaction is going to do whatever it needs to get back into equilibrium. And whatever you do to one side, it's going to affect the entire reaction. Okay? So the next one is temperature. Temperature is, you well know, is based on heat, all right, kinetic energy. So the thing we need to know about this is which way does heat go? Is heat a product or a reactant? So for an endothermic reaction, endothermic means I'm absorbing heat. So heat would be a reactant, right? Because I need heat in order to start my reaction. So endothermic means heat is absorbed as a reactant. Exothermic is the exact opposite. It's heat being given off. So if I have my reaction and heat is being as a product, that means that my reaction is exothermic. So heat as is exothermic is heat as a product. All right? And then the same rules apply just like we talked about with equilibrium. So if I look at this equation, heat is a reactant. So I know that this reaction is endothermic. I can tell that by where the heat is. All right? And then it says, okay, so if I place a system in an ice bath, well, what does ice bath do to my heat? Okay, it actually decreases the heat, right? If I put it in an ice bath, the heat is going to go into my ice bath and I'm going to decrease my heat. If I decrease my heat, then I have just lowered my reactant side, and so equilibrium has to shift to my reactants and make more reactants. Now, if I place the system over a Bunsen burner, heat is actually going to increase, correct? Because I'm putting it over a flame, heat increases. And if my reactants are increasing, then I have to shift and make more products. So whichever side heat is on, if you mess with the heat, you're going to have to fill those gaps just like we did with concentration. All right, the next one is pressure. Okay, so pressure is very special. First of all, pressure only deals with gases, all right? So if you have a solid or a liquid in your equation, we can't determine how pressure is going to affect equilibrium. But if we have gases, then we can look at the total number of moles on each side, and we can tell which way you're going to shift. So let's start with this example. Which side has more moles of gas, products or reactants? So I have 1 mole of nitrogen and 3 moles of hydrogen. So on my reactant side, I have 4 moles. Over here, I only have 2. So my reactants have more moles. So if I increase the pressure, which side will equilibrium shift to? Well, just like you don't like being in pressurized situations, neither do chemical reactions. So if I had a lot of pressure, would I want to be a high number of moles or would I want to be a low number of moles? If you said low number, you're correct. The less moles there are, the less bumping that's going to occur between them, and the reaction is happier, right? The molecules are happier. So if I increase pressure, equilibrium is going to shift to the side that has less moles, okay? Because that's going to relieve some of that pressure that's been put upon it. But if I decrease pressure, then I've got all of the space in the world, they can be happy, and my equilibrium is going to shift to more moles. Oops, that's supposed to be an M. There we go. More moles. So, equilibrium. Increase pressure, I'm going to shift to the side that has less moles, or less molecules. Decrease pressure, I'm going to shift to the side that has more moles, because my equilibrium can handle it, and it'll equilibrialize until they're both back to that state that they like, okay? Alright, volume is the same as pressure, as in it only deals with gases, okay? So if I have solids and liquids in there, this principle does not apply to them, just like pressure. So it's the same thing that we talked about with pressure. If I look at my equation, I'm going to see who has more moles. So if I look over here, I have 2 hydrogens and 1 oxygen, so I have 3. And then I have 2 on my product side. Now, if I decrease the volume, okay, if I decrease the volume of my container, that means that they're going to be in a more enclosed space. So if I decrease that volume, then I'm going to be shifting to less moles. In this case, that's the products, okay? Because I'm pulling them closer together, and so they're going to stay in the least amount possible. But if I increase the volume and I give them as much space as they want, they're going to shift to whoever has more moles. Now for both pressure and volume, if I have the same amount of moles on both sides, will there be a shift in equilibrium? The answer is no, there won't. So if I have an equation, in my fake equation right here, I have 1A goes to 1B. Now they're both gases, so pressure and volume will affect the equilibrium. However, both of them have 1 mole on this side and 1 mole on that side. And so therefore, pressure and volume are not going to shift equilibrium because both of the sides are already equal when it comes to moles. So changing the pressure and changing the volume are not going to change my equilibrium. In order to change this equilibrium, I would have to change concentration, or I would have to change temperature. Okay? And then there's one more thing that we need to go over. Okay, so KEQ, we calculated this with equilibrium concentrations, correct? Products over reactants, the concentrations at equilibrium. So if I'm switching, or if I'm shifting equilibrium, will KEQ change? Think about that for a moment. Okay, so if you thought about it, products and reactants at equilibrium, the concentrations are always constant. When I'm shifting equilibrium, I'm causing it to go out of whack until it gets back into equilibrium. So KEQ does not change when we shift equilibrium, because KEQ is the ratio at equilibrium. All right? Now that we've gone over Le Chatelier's principle, I want you to try numbers 1 through 3. Remember to make the equation equal, and good luck!